Hi guys, so today I'm going to be going through using the Ensemble n-sub-epidemic framework toolbox. So the first thing you're going to want to do is navigate over to the GitHub page. On here, you will see some descriptions of some of the functions available as part of the toolbox, along with this Ensemble n-sub-epidemic code folder. So taking a look at the folder, within it, you will see multiple MATLAB files, which we'll go through in a bit, and then an input and output folder. So taking a look at the input folder, when you download this toolbox, these will come preloaded as part of the toolbox. This also contains the code the data we will be using for the tutorial today. And then you will also see in the output folder, there are some files in here as well. These are just some preloaded output that come when you download the toolbox. You will need to create your own input and output folder when you have this downloaded, and then in the input folder, that is where you will place your data you are wishing to use as part of the toolbox. So to download that folder, what you need to do is navigate over here to the code button, and then you will click download zip. And you'll see a zip folder show up in your downloads. What you'll need to do then is move that to a place in your computer where it will be easily accessible. For me, I have mine located in my desktop. So if I go to unzip this folder, directly I get an error. So you guys might get this error as well. And what you can do to get around that is go into MATLAB. And then you will navigate to where you have that zip folder. So for me, mine is in my desktop. We can see it right here. And I've already unzipped this, but if you run into the same error that just showed up, what you will do is double click on the Ensemble n-sub-epidemic framework zip folder, and then it will immediately unzip for you in the location or where it's located. So once it is unzipped, what you can do is right click on the unzip folder, and then you'll want to add that to your MATLAB path. So you'll go to add the path and then selected folders and subfolders. So now you're ready to open that up in full. Now, as you can see, this looks very similar to with what we were looking at beforehand in the GitHub page. So taking a look first at our inputs, what we're going to do is look at one of these TXT files. So all of your input files that you put in here with your own data and what you'll see in here are all .txt files. And then here, each column represents a different area. So in this case, we have 52 different columns representing the different states in the United States, along with DC and then deaths on the national level. And then looking at the naming scheme here for the file, how this needs to be set up is, first, if you're working with cumulative data, you need to put the word cumulative here. If you're not working with cumulative data, rather you're working with incident data, you can leave that cumulative off. And then next you enter the time period associated with your data. So are you working with daily data, weekly data, or yearly data? And then the name of the disease you're working with. Then the type of data you're working with. So here we're working with deaths data. Then what is the generalized region of your data? So in this case, the USA for us. And then the state here is the very last date of available data that you have in the specific file. So here that is 5/11/20. So this file would contain cumulative daily death data through 5/11/20. Let me close that out. So next, taking a look at the different MATLAB files we have here. The ones of particular interest to us are the options.m, the options forecast, the plot forecast, the plot fit, and then the plot rankings files. So what we are going to take a look at first is the options.m file. So this is where we're going to make our changes and about or indicating things about our data, what type of parameter methods we want used in fitting our data, and all sorts of other different things. So looking first here, we can see our where we declare our global variables, and that will remain the same. Next, we're going to enter some parameters related to the data. And here we can just see a little bit of description on how to make sure your data is set up and going through the same naming scheme we just went through looking at the txt file. And then the first thing we come across where we may need to make changes is our cumulative 1 input. So this is a binary variable which indicates whether our input file contains cumulative data or not. So for the purposes of this tutorial, as we're working with cumulative data, we will leave this 1. Next, the outbreak X input, this indicates the area or group of interest. So the number here corresponds to the column of data within the txt file we want to work with. So in this case, we have this set as 52. So this indicates we want to work with the very last column of data we were looking at in the txt file, which in this case represents COVID deaths on the national level. The CAD date 1 parameter is the date used in naming the file and should be the most recent observation within the data file. So in the data that we're using for this tutorial, the most recent observation included was 5/11/2020. So that is the data or date we enter here. So again, that means we are working with this input file here, the 5/11/20 input file, or I'm sorry, the 5/11/2020 input file. And then our CAD region indicates the geographical region associated with the overall time series. So here, the USA. Our CAD disease indicates the disease we are working with. The data type is where we indicate the type of data we're working with. So again, here we're working with deaths. So this is entered as deaths. And then DT, this is where we indicate the time structure of our data. So what I mean is this is where we enter if we're working with daily data, weekly data, or yearly data. For the purposes of this tutorial, we are working with daily data. So this is where we would enter a 1. So we enter a 1 here to indicate daily data. If we are working with weekly data, we would put this or put DT as 7. And then if we're working with yearly data, we would enter 365. This next bit of code here, this is just setting up our CAD temporal variable based on what value is entered for DT. So here, as our DT is equal to 1, our CAD temporal variable is then going to equal daily. And if it was 7, it would equal weekly. And then if our DT was 365, our CAD temporal would equal yearly. So the next parameter we're taking a look at is our date vec first 1. So this is the very first data point within our time series. So meaning what is the earliest day, week, or year of data available within the input file. And for us, this is February 27th, 2020. And then finally, within the parameters related to the data section, we have our date vec n1 variable. So this is where we indicate the most recent input data file that we have. So for example, if we only had one data file, so let's say that 5/11/20 data file or input file we're working with in the tutorial, we would enter that date here. But as we have multiple input files available to us, we enter what is the most recent one. So in this case, that is May 9th, 2022. And then this file is used when we're assessing forecast performance, which we'll go over in a little bit. So on to our next section here, the adjustments to our data. So here we have 2 parameters, our smooth factor 1 and then our calibration period. So our smooth factor 1 input here allows us to smooth out our time series by using a moving average. So smoothing is generally used when there's a lot of noise in the data, so this is sometimes seen with weekend effects. And here's where we indicate the span of our moving average. So for this tutorial, we are going to be using a 7-day moving average to reduce the noise within our data. So we enter a 7 here. However, if we were working with, let's say, weekly data, or we didn't want any smoothing, we would enter a 1 here to indicate we do not want any smoothing within our data. And then our calibration period 1, this is where we indicate the number of recent data points that we want to use to calibrate our models. The calibration period exceeds the length of the inputted time series. This will then be set to the maximum length of available data. So let's say if our input file did not contain 90 days worth of data, then our calibration period will autocorrect to how many dates of data are available. However, in this case, we do have 90 days worth of data available, so this will remain 90. So this means we are calibrating our model with the most recent 90 days of data. We're working with weekly data, that 90 there would calibrate to 90 weeks, and if we were working with yearly, it would correspond to 90 years. So the calibration 1 value here corresponds to whatever type of, whatever value for DT that you enter here. So looking at the parameter estimation in bootstrapping section, so first we see our method 1. So this parameter is used to indicate the type of method we want to use when estimating the set of model parameters. And for this tutorial, we're going to be using nonlinear least squares. However, you can see there are different options you can choose from. And then our dist1 parameter is used to indicate the type of error structure to be assumed in fitting the model. So again, in this tutorial, we will be using a normal error structure as indicated by the 0 here. Again, however, there are multiple options you can choose from for that parameter. And finally, our num start points. So this is where we indicate the number of random initial guesses of model parameters to search through for the best fit parameter estimate. So we'll leave this set as 10. And then finally, our B here is the number of bootstrap realizations we're using to characterize parameter uncertainty. So here we have this set to 300. So next here in the n-sub-epidemic growth model section, the first thing we see is our n patches fixed. So this parameter indicates the maximum number of sub-epidemics considered in the epidemic trajectory. So here we have this set to 2, meaning we're going to be considering a maximum of 2 sub-epidemics in the epidemic trajectory. And then this top model's X here, so this is used to specify the number of top ranking models that will be generated and used to derive the ensemble models. And if we look below here, so right here, we can see that if the maximum number of sub-epidemics considered is equal to 1, so if this is equal to 1, then our top model's X will self-correct to equal 1. Finally, our flag 1 parameter is where we indicate the desired sub-epidemic growth model we want to use when fitting our model. So for this tutorial, we're going to be using a generalized logistic growth model, or GLM model, as indicated by this GLM here. But we have different options we can use, and we can change that here by changing this GLM to represent one of the options listed here. And then finally, we have our onset mixed variable. So this is where we choose if we want the onset timing of the sub-epidemics to be fixed at time 0 or not. So in this tutorial, we will be running it both ways. So we'll have it fixed and not fixed. However, we're going to start with it not fixed, so our onset fixed equal to 0. And then looking here, we can see that when the onset is fixed, if the number of best fitting sub-epidemic models is greater than the number of sub-epidemics being considered, the code will then self-correct where the number of top models and the number of sub-epidemics considered will then equal each other. So as indicated here. So now we've gone through our options.m. So next thing we're going to want to take a look at is our options forecast. So this is the second file where we will be making any changes, and we will only make any changes in the options.m and the options_forecast files. So first we see our get performance here. So this is a binary variable to indicate if we want to calculate forecast performance metrics or not. Next is our delete temp files which is equal to 1 right now. So this is also a binary variable indicating whether or not we want to delete the forecast.map files that will show up when we're producing our forecast. And then our forecasting period. So this is where we indicate how many time units ahead we want to forecast. So in this case, we have it set to 30, meaning we want to do 30 days ahead forecast. Finally, we have our weight type here. So this is where we set the weighting scheme for Ensemble models. So as you can see by the comments here, there are many options. And for the purposes of this tutorial, we will be producing weighted Ensemble models based on the weighted combination of highest ranking sub-epidemic models based on relative likelihood. So looking here, that means we want to change our weight type to equal 1. So now that we've made our changes in our options.m and our options.forecast.m, we are ready to fit our model. So what we need to do is open our run fit sub-epidemic framework.m. So here, this is the file that you'll want to run before using the plot fit, plot rankings, or plot forecast files. So this is used to fit your model or fit the models to your data based on the options you choose in the options.m file. There are 2 different ways you can run this. So you can either directly run it from the file and hit run, or what you can do is highlight this up here. So the run fit sub-epidemic framework, and then we have our outbreak pass and CAD date 1 pass. So if we copy that and paste it in our command window, we are going to be making a few changes in here. So what we're going to change here is we're going to change our outbreak pass to 52. And then we are going to change our CAD date pass to this date here. So we're going to change it to 05/11/2020. So if I ran that, I'm going to let it run for a second. You'll see some outputs start to show up. For the purposes of this tutorial, I am not going to run that in full because it does take quite a while to run. But I do already have that pre-run for us. So let's take a look at some of our outputs. So here you'll see a couple of files. So you'll see some called ABC, and then a couple also called modified logistic patch files. So within these file names, you can see a lot of the parameters we selected in our options.m file, and these are the files that are used when plotting model fits, deriving parameter estimations, generating short-term forecasts, and quantifying the calibration and forecasting performance metrics. So now that we have fit our model, we are ready to produce our forecast and get some output. So if we go to our plot forecast sub-epidemic framework, so again, similar to our run fit, we can run this 2 different ways. We can either directly run from this file, or what we can do is highlight this plot forecast sub-epidemic framework up here. Paste that here, and then enter a couple things. So this outbreak pass, this represents the outbreak number that we entered in our options, so 52. Our CAD date pass is that May date again, so that was 05/11/2020. 2020. And then our forecasting period pass, this is our forecasting horizon we indicated within our options forecast. So here, 30. And then our wait type 1 pass is the wait type that we indicated in our options forecast file. So here that was 1. So if we run it this way, what will happen is we manually enter those inputs there, and then the remaining inputs will be taken from the options.m and options_forecast files. Or if we run directly from here, all options that we've selected in the options.m and options.forecast.m files will be used. So we'll let this run for a moment. And we'll start to see some outputs show up. Take too much longer. So what is showing up here is we are going to get some figures as part of running this output along with some CSV output. And you will get figures for each of your top ranked models along with the generated ensemble models. And it looks like it just finished. So let's take a look at some of our output. So here, this shows the sub-epidemic profiles of the 30-day forecast derived from the top-ranking sub-epidemic models from the daily curve of COVID-19 deaths in the USA from the dates we selected. And then through, it doesn't show it exactly here, but it's through June 10th. So the blue and red curves represent the different sub-epidemics of the epidemic wave profile. And then this gray curve here corresponds to the overall epidemic trajectory by aggregating those sub-epidemic curves. So by aggregating the red and blue. And then this vertical line here indicates the start time of the forecast and then separates our calibration here from our forecast period. And as you can see, we get one of these for each of our top ranked models. So for our top ranked, second ranked, third ranked, and fourth ranked. Then looking at our other figures, so then we get these two figures here. So let me make these a little bit bigger. So these show our model fit along with our forecast and then overlaid with our observed points during the forecasted period to show our 95% prediction interval coverage. So the solid line here, which is a little bit hard to see, the solid red line, this represents our model fit. The gray is our 95% prediction interval. And then our points are our actual observed points. Then you can see we get one of these for each of our models. So for each of the ranked models and then each of our ensemble models as well. And then finally, we get two figures that look like this. So we get this, and then we get that figure. So the background figure with the ensemble, where it says ensemble model. So this is the forecast performance metrics derived from the ensemble sub-epidemic models for the daily curve of COVID-19 deaths we've been working with. And then the results of this graph in the background here, this is also saved as a CSV output. And then similar here, this is the performance metrics for the top ranking sub-epidemic models, which is also saved as a CSV output. we'll take a look at that now. So you will find that output within your output folder in your toolbox. So you can see here, I have multiple CSV files that are new. So the first couple here, so right here, these are our forecasts we get. So as you can see, a lot of our parameters are saved within the name. So we're working with onset fix 0, flag 1, we're working with method 0, we're doing 30-day forecasting horizon with our weight type 1, daily coronavirus deaths, so on and so forth. So let's take a look at one of these files first. Then you might get an error just because the file name is a little long. If you get that error, what you can do is just rename it to something that you will know what it means. And then taking a look here, we can see the year, the month, and the day represented, or what our data, median, lower bound, and upper bound are corresponding to. The data here, this is the observed data at each of these dates. The median is our model fit, and then our lower and upper bounds are our lower and upper 95% prediction intervals. This includes our model fit and then our forecast. So the last 30 lines here represent our forecasted points. Then we also get two files for our performance metrics. So let's take a look at the first one here. We'll just take a moment to pop up. So here what we can see is our four performance metrics that we're working with: our mean absolute error, mean square error, our 95 prediction interval coverage, and then our weighted interval score. And then we get those metrics for each of our ensemble models here, our second, our third, or our 2, our 3, and our 4. And we also get something similar for our top ranked, where each of the rows represent our different top ranking models. So now that we've taken a look at our forecast, we can also plot our model fit and get performance metrics for our model fit. So here what we're going to do is run this directly. So we can either run this directly, or similarly with the other files, we can run this by using our console. So same thing, you highlight this up here, copy it in our console, enter your outbreak path. So in our case, it would be 52. And then the CAD date you're working with. So for us, that May 11th date. Or you can run it directly. So we'll let this run. So this should just take a moment. Awesome. So this is all done running. Let's take a look at the different plots we got with this. So as you can see, we have quite a few. So first, looking at this shows I'll let it adjust for a moment, the model fits of our top ranking sub-epidemic models to our curve. So looking at this, it looks like overall the sub-epidemic models capture the entire curve well. And then here we can see our red line represents our model fits. And then the 95 prediction interval is indicated by the dashed red line shown here. And then the points are our observed points. We also see our sub-epidemic profiles shown in these center panels, where the red and blue curves represent our two sub-epidemics. And then the gray curve represents the overall trajectory of the epidemic, from aggregating the two sub-epidemics. And then the black circles here correspond to the data points. And we also get our residuals over here. And we also get a few of these plots. So these are our parameter estimations. What this graph shows is our parameter estimations for the first and second sub-epidemics used in fitting our model for the first or top-ranked sub-epidemic model after fitting the modeling framework to our curve. So the parameter estimations for both sub-epidemics look well-defined as indicated by their relatively narrow bootstrap confidence intervals. And then finally, similar to what we get with the forecast performance, we also get a plot showing our metrics, and this is also outputted as a .csv file. And then finally, we get similar parameter estimations for our second ranked model, for our third, and then for our fourth ranked model, similar to what we just looked at with our top ranked model. Taking a look at then our outputs, so you can see we have a couple new CSVs that are outputted. So in this case, it is our performance calibration. So this performance calibration here, it shows, let me change the file name and I'll show you what it shows. So here we can see our performance of the model fit for our top-ranking models, and the same metrics are used here, the MAE, MSE, our 95 PI coverage, and then our weighted interval score. And the last thing we're going to take a look at, so now that we've done our plot fit and we've looked at our model fit, finally we're going to take a look at the plot rankings file. So here, this file can be used to plot the mean model fits of the top ranking models, including their sub-epidemic profiles and associated quality of model fit metrics, including AIC, relative likelihood, and the evidence-based ratio based on the inputs selected in the options.m file. So like the other files, we can run this two ways. We can either run it directly or copy this function here, put it in our console, and insert our outbreak path, so that 52, and then our CAD date, so that date we're working with. Here, I'm going to run this directly, so this will just take a moment. Then we get some file outputs. So taking a look first here, this shows our mean model fits of the top-ranked sub-epidemic models, and they are calibrated to the daily curve of COVID deaths we're working with. So the blue and red solid lines correspond to the individual sub-epidemic curves, and then the solid black line represents the overall aggregated epidemic curve. And then our legend here indicates the number of sub-epidemics involved with each model, and then the value of the CTHR parameter. Then the other graph we get here, so this shows our AIC, relative likelihood, and evidence ratio for each of our top-ranked models. And finally, the last thing here, as I said earlier, we can run this also with a different onset fixed. So here we have this equal to 0. We can also make this equal to 1 and repeat all those steps and get slightly different looking figures. So that is all that there is with the sub-epidemic toolbox. Thank you.